Let's start on the right-hand side. Now, the right-hand side is just a very, very simple kind of, okay, here are a load of functions, okay, so like y equals something with x in. Can you differentiate them? Now, just to make sure we're all on the same page, because like I say, this was done a long, long time ago, or relatively long time ago, what am I asking you to do if I'm asking you to differentiate? What does differentiate actually mean? Can anybody remember? What does this word differentiate actually mean? It literally asks you for the rate of change. Okay? So the rate of change. In other words, it says, imagine this is a function. I don't know, x could be time and y could be the amount of money. Okay? So it literally says, you tell me how long you've left your money into a bank account for, and I will tell you how much money you will have. Okay? So you give me time, I'll tell you the amount of money. Okay? Or it could be anything similar to that. Now, what I'm asking you to do, if I'm asking you to differentiate, is it's asking you how quickly is your money changing at a particular point in time. Okay? Now, this clearly isn't a particularly nice function. What type of function is this? Cubic. It's a cubic function, right? So it's not a terrible function, but it's not a nice function, not, say, for example, like a linear function. If I gave you a linear function, for example, something like this, and if I asked you y equals 3x plus 2, and if I asked you how quickly is my, I don't know, money changing at any particular instant, what would you tell me? If I told you that x is time, and the amount of money which you have is just simply 3 times whatever time point you're at, add 2, how would you find how quickly your money is growing? Would you be happy that it's just simply the gradient? It's just simply the gradient. That's literally what the gradient tells you. It's how quickly is something changing with respect to, in this case, x, in this case, time. Okay? So what I'm literally asking you to do, if I'm asking you to find the rate of change, is find the gradient. Find the gradient. Yeah, does that ring some bells? A little bit? Okay, a little bit. So differentiation is simply to do with finding the rate of change or finding the gradient. Now, of course, this is a cubic curve. It probably looks something a little bit like this. Okay, something a little bit like this. So clearly, if I'm asking you to find the gradient, would you be happy that the gradient is different at different points in time? Because what line is the gradient to do with? The steepness, yeah, exactly. So for example, the steepness like that, yeah? What line is that? What do we call that line? Slope. Well, the slope is how steep it is, but in relation to the curve, it's the tangent line, yeah? So another way of thinking about this is to do with tangents. Are you happy? So like before Christmas, I gave you like lots of ideas in quite a short space of time because I said there's quite a lot of things going on here. Yeah, differentiation is to do with rate of change, how quickly something is happening, which in turn means that I'm asking you to find the gradient. And because it's a curve instead of just a straight line, the gradient is related to the tangent. Is that okay? Yeah? Okay. So, short question then is, how do I differentiate this thing? Can anybody remember?
By multiplying the number next to the, for example, for the 4x power of 3, we multiply 4 by 3 and then we subtract 1 from the power.
Absolutely right. So if you didn't quite catch that, you look at each term individually, so you look at the bits in between the plus and minuses, and the rule is you bring the power down, you reduce the power by 1. Okay? So I would write my derivative, in this case dy by dx, you happy? dy by dx, right? Would be equal to this first term, 4x cubed, I bring the power down, so it would become 4 times 3, which is 12, and then I go x to the power of, reduce the power by 1, it becomes 2. Is that okay? So you bring the power down, you reduce the power by 1. That's all there is to it. Happy? Okay. So then they need to look at my next term. Well, what's the power of the x in this case?
1.
It's 1. So bring the power down, 7 times 1, that's 7. Then I get x to the power of 0.
1.
Exactly, because x to the power of 0 is just 1. So I'm just going to write that as 7. You happy with that? Good. What about this one? The 2 at the end.
Disregard it.
We do,
Right
but
plus
why?
C.
Sorry?
Right plus C.
Not yet.
B.
Not yet. I think you might be confusing it with integration. What do we do with this thing? We do disregard it, but why? Convince me.
Because it doesn't have an X.
Doesn't it? We don't write it because the power of x is
0.
perfect. There is an x there, it's just x to the power 0, because that's 1, okay? So watch what happens, bring the power down, well 0 times 2, I don't care about what happens next because I know 0 times anything is just 0. So just a plus 0 there. Are you happy with that? Okay. So think about it. I started off, let me take it back to what I originally gave you. Y equals 4x cubed plus 7x plus 2. Okay, that was my original function. I asked you to find the rate of change. I asked you to differentiate it. Okay, and you get this. Now this isn't just a number, is it? It's a function. What does this function actually mean? What does this function actually mean? 12x squared plus 7.
The rate of change.
It is the rate of change, but why has it still got x's in? Why is it not just a single number? Like if this number was just 5, then you're just basically saying that at any point in time, my rate of change is 5. In other words, if I move across by 1 unit, I move up by 5, right? But this isn't. This has still got x's in. Why? Think about it. It's a cubic function, okay? So it looks something like that. Are you happy that if I'm looking at the rate of change, for example, at this point over here, the rate of change will be quite steep, yeah, and positive, okay? Whereas if I look, for example, at this point here, the rate of change is still steep, but it's in the opposite direction, okay? And if I look at this point over here, for example, the rate of change will be positive, but perhaps not quite as steep. So in other words, my rate of change, how quickly my function is changing, is different depending which point I'm looking at. Are you happy with that? Okay, so therefore, it makes sense that my rate of change function still has an x in, because you still need to tell me which point do you want to find the rate of change. Is that okay? Yeah? Okay, good. So essentially, because it's still got an x in, it's because the rate of change is different depending on which point you're looking at. Okay? So we would call this the rate of change function, or the gradient function. Okay, fine. All right, okay, so that's kind of an overview of the ideas. Let's just get on with how we do the next 3, or the next 4. How do we do question 2? What's the problem here?
We just multiply the x power of 3 by 8, but we need to add the negative sign.
Okay, so what would this first term become?
8x power of negative 3.
Okay, so first things first, to do any differentiating, we need to rewrite, okay? So we need to rewrite it in the form of this, or this, or this. Okay, so it needs to be something x to the power of something. 8 over x cubed, that's not looking like that. But that's okay, we know our laws of indices. If we have an over x to the power of something, that just becomes the negative power. You happy with that? Okay. Everything else is fine though, still write it. Now we're in a position where we could differentiate. So what would dy by dx be equal to? Yeah, good. So you bring the power down. Negative 3 times 8 is negative 24. X to the power of, reduce the power by 1, negative 4. Good. Somebody else, what would 7x to the power of 4 become? 28x. Good. 28x to the power of 3. Happy with that? Now, one thing which I would say, if you left your answer like that, it would be totally fine. However, just a nice thing which I like to do, you see here, this has got negative powers. This has got negative powers. Did the original thing that I gave you have any negative powers in? So always try and leave this in the form that you got given the original function in. Okay, it's just polite, it's just easier to deal with, all right? So what would this be if I left it in the form with fractions?
Negative 24 over x power of 4.
Good, negative 24 over x to the power of 4, and then you're happy, this is just fine. So plus 28x to the power of 3. You all happy with that? Good, excellent. What about the next one? Let's move through these slightly quicker. What's the next one? How do we deal with this?
First of all, multiply the brackets and
Good. Why can't we just do it directly? Why do we have to multiply the brackets out? Why do we have to expand the brackets?
because it's not an add. It's not.
We don't know how to deal with products, do we? We don't have to deal with multiples. So we have to multiply this out so it's got like something plus something plus something. Okay, good. If we expand this out, what do we get?
6x squared.
Good.
Negative 12x.
Negative 12x, perfect. If we differentiate it, what do we get?
12x. Negative 12.
Minus 12, perfect. You happy with that? Good, okay. What about number 4?
We bring the power to up and then we multiply it by the rest.
Yeah, we absolutely could. So we could deal with this thing on the denominator and realise that this, so this is basically something over 3x, could be written as x to the power of negative 1 if we wanted to. Does anybody do it a slightly different way? Yeah, exactly. Because you've got two things on the numerator which you're dividing by the same thing, so you're taking 27x to the power 4 and negative 9x and dividing both of those by 3x, do that, okay? Yeah, so it just depends which way you see easier, right? So in other words, I'm thinking about this as 27x to the power 4 divided by 3x minus 9x divided by 3x. So I'm dividing each individual thing by 3x. Happy? Good, okay. So what do we get?
9x power 3.
Good, 9x to the power 3
Negative 3.
minus 3. Perfect. So if I differentiate it, what do I get?
27x squared.
27x squared. Just that, because of course this is just a constant. It's got x to the power 0. Bring the power down, it just becomes 0. Perfect. Okay. What do we get on this one then? Number 5. How do we deal with this?
Same as, oh.
Multiply the brackets first and then divide.
Absolutely right. Multiply the brackets out first, then you can just treat it the same thing as you did question 4. All right? So what do you get if you expand the brackets out, Batikon? Could you do it now? So just multiply the brackets out. Good. Yep. 7 times 8.
17 minus 14. So it's like
Not quite.
50, 56. Yeah.
Good. 56 x to the power of 6. Good. Good, because there's no x there. Perfect, well done. Okay, all divided by 4x squared. But of course, you can just think about this. I'm just dividing every single term by 4x squared. All right? So what do I get?
7x power of 8 over 4x squared. So it's like a 7
Yeah.
over 4x power of 6.
Perfect. Okay, you all happy with that? So I'm just doing 7x to the power of 8 divided by 4x squared. 7 divided by 4 is just 7 over 4. Okay. Then I've got x to the power of 8 divided by x to the power of 2. That's got to be x to the power of 6. Happy? Okay, somebody else then. What do I get for the next one? 56x to the power of 6 divided by 4x squared.
Plus 14x to the power of 4.
Perfect. Well done. And then what do I get for the last one?
Negative 21 over 4 x to the power of 3.
Yeah, good. Well done. Over 4. Yeah. Well done. You all happy with that? Okay. And then I can differentiate it. It looks a bit horrible, but remember we've just got something times by x to the power of something. Okay. So what do I get here? What do I get for my first term?
21 over 2 x to the power of 5.
21 over 2x to the power of 5. Good. Then the next one.
56 x to the power of 3.
Good. And then the next one.
Negative 63 over 4 x to the power of 2.
Excellent. Well done. Are you all happy with that?